Mr. Chairman, ladies and gentlemen, thank you for your welcome. I come to you not knowing a word of Portuguese, and so I'm trusting that what Professor Molly has just said is complimentary and not too derogatory. Thank you for your welcome. As well as bringing myself and my suitcase from England, I'm afraid I've also brought an English cough and cold, so please bear with me if I drink some water in the middle of my talk. The title of my talk is Precision Agriculture, Meeting Current Challenges. So just where did precision agriculture start? Well, we could go back 30 years to the National Soil Dynamics Laboratory in Auburn, Alabama, where three scientists made this statement. Future machinery used in production agriculture will be automatically controlled to prescribe cultural practices based on soil, crop and climate. Some soil and crop information may be sensed on the go and stored in a computer on board the prime mover or field machine. The computer in turn could be programmed to make real-time decisions based on this information to control cultural practices such as fertilizer, herbicide and pesticide application. Important to this concept is a general spatial position sensing system that can pinpoint the position of a machine in the field at any time. But this really was quite a visionary statement when you bear in mind that in the early 80s, electronics had hardly come onto field machinery at all. And we used to talk in terms of electronics for agriculture having to be to a higher specification than military electronics because of the bad environment. And they even had this vision of a positioning system. And again, in 1980, we were talking about GPS only having just been established, and that, of course, only for military use. And so this really was quite a visionary statement of precision agriculture. But actually, we could go back a lot further. We could go back 2,000 years to the story that Jesus told, the parable he told of the farmer who went out to sow his field. And in that story, it states that the farmer, of course, broadcast his seed, as he did in those days, and that some seed fell on the path, some seed fell on stony ground, some seed fell amongst weeds, but some fell on good soil. And of course, it was only on the good soil that a good yield was produced. Now, you might well say, isn't that the very antithesis of precision agriculture? But was it? Didn't that farmer use the technology that he had available to him, and that technology with his eyes and his hands, to sow as precisely as he could? I'm sure that he sought to minimise the amount of seed that fell on rocky ground and amongst the weeds, and maximise the seed that fell in good soil. Precision agriculture? Interesting question. So, of course, the human eye is wonderful, but it has its limitations. So, maybe in those days, with very small plots of ground, yes, they might know something about the variability within the field, within that little field. Have a look at this, which is an area of land of 60 hectares in Denmark, which in 1775 was farmed as, and no doubt, the farmer sowing his little area of field knew something about the variability within that field. But within 100 years, that was being farmed as just 5 fields. And certainly for those bigger areas, there's no way the farmer could tell about variability. 100 years on, 1995, it was farmed as one area. It's just impossible for the farmer to be able to tell the variability in that field, other than in very qualitative terms. And you know, if we're thinking about when did precision agriculture start, even yield mapping, which we think, well, that came in about 20, 25 years ago, that goes back even further, because there at Rothamsted Experimental Station in the UK in 1925, they were doing hand harvesting and producing yield maps, drawing them by hand with a grey pencil, and looking at the variability. Improved slightly in 1938. They were actually using coloured pencils, but you know, so there was yield mapping going on even then. But of course, what's brought in the modern concept of precision agriculture is global navigation satellite systems. And that's made all the difference, of course. When we first started researching GPS for use in agriculture in the early 90s, of course, GPS equipment had it carried around in a suitcase, it was so big. Now, well, I got it in my pocket, as I'm sure all of you have, a smartphone. Every smartphone has got a GPS engine in it, and those GPS engines go on your little finger. It's quite an incredible increase or change in technology. And so in many ways, precision agriculture can now be described as mainstream. So after all, auto guidance is very widely practiced by farmers throughout the world. Soil is characterized by soil electrical conductivity mapping and such other means. Variable rate nitrogen application is practiced again in many areas. One might question how it's being practiced, but it is being practiced. There's traceability all the way from the field right through to the consumer. Soil sampling and mapping is routine, even to a reasonable degree of resolution within the field. And of course, yield mapping, whatever yield mapping might tell us, has been practiced now for a good many years. Now, within our world, there are serious global challenges facing agriculture. And the question to address this morning really is, how can precision agriculture help to ameliorate some of those challenges? Go back to 2008, the Farm Foundation in the US produced a report proposing a 30-year challenge. And they stated, agriculture has always been under pressure to feed a growing world. But the problem today is compounded by competing bioenergy demands, increasing competition for natural resources, climate change and income growth. Booming income growth in many developing countries causes consumers' diets to shift away from traditional staples in favour of livestock products. At the same time that more and more output is needed, consumers hold the agricultural sector to increasingly higher food safety standards. And then another report was produced by the UK government, it was about 2011, 2012, entitled The Future of Food and Farming, Challenges and Choices for Global Sustainability, which made the point that with 900 million people going hungry, 13% of the world going hungry, with 1 in 7 having insufficient food, there's need for us to face up seriously to the challenges. And they put before in this report 5 challenges. The challenge A, balancing future demand and supply sustainably. And second challenge, addressing the threat of future volatility in the food system. Third challenge, ending hunger. Fourth challenge, meeting the challenges of a low emissions world. And fifth challenge, maintaining biodiversity and ecosystem services while feeding the world. And then within the European Union, the Standing Committee on Agricultural Research has produced a number of reports, and their second one stated world population will increase to an estimated 9 billion people in 2050, while agricultural productivity has been slowing down over recent decades. Rising income levels in emerging countries will shift diets to include more protein-rich food and will increase energy demand. At the same time, resource constraints and climate change severely limit the world's capacity to expand food production. Hence, there is a serious threat that food demand will not be met in 2050, leading to more hunger and political instability. Now, in the face of those reports, we know that there's a lot of research going on in precision agriculture. A lot of you, of course, are involved yourselves in research in the topic area. And a lot of that research, of course, is published in conferences such as this one, and other ones such as the European Conference, which met last year in Spain, the Asian Conference, which met in Korea, and the International Conference on Precision Agriculture meeting only this last July in Sacramento, California. And of course a lot of that research that's reported in those conferences is also published in the journal Precision Agriculture, of which currently I'm co-editor-in-chief, and of which it's growing in importance, which is reflected in the fact that it now has an impact factor of just over 2, so it's been increasing each year. It's very encouraging, but it does mean it's an important journal. And it's interesting actually to look at the topics that are covered in Precision Agriculture Journal. This is just looking over 3 volumes, 2011 to 2013. And you see there that in fact most topics, or the topic most covered has been remote sensing, both multi and hyperspectral imaging, followed by papers on crop and soil spatial variability, crop yield, going all the way down. Notably actually, over the far side, you'll see it goes down to soil sensors, and we say, well, sensing soil parameters actually surely is one of the most important things that we need to do, and yet how few papers there are on it. No doubt tomorrow Robin Gebbers will expand on that and give us some positive views. Interesting also to look at the range of crops that are covered within the journal. So here again, over a 7-year period on the journal, you'll see, not surprisingly, that wheat, corn, maize are the most favourite crops to be covered. Interestingly, precision viticulture comes third there. And there's some very good work going on in various parts of the world. I think of papers coming in from Spain in particular on precision viticulture. And then going all the way across a whole range of different crops. What I'd like to do is to look at 8 different challenges and just give an indication of how precision agriculture can begin to meet some of those challenges by just giving as examples some of the papers published in the conferences and in the journal. So first challenge is food security, defined as stable access to sufficient and safe food supplies. Already stated, 900 million people in the world going hungry, 1 in 7 have insufficient to eat. So very important that we meet that need for food. You might not think, I suppose, that peanuts are the staple, but it is in some ways. And here we've got a paper by Verde and his colleagues, which was reporting on site-specific management of limiting nutrients in peanut. And what they looked at was the effect of calcium, and they computed a response function for the effect of varying calcium application, lime application. And in the case of that, they gained a yield gain of 374 kilograms per hectare, and with nitrogen, an increase in 212 kilograms per hectare. So quite significant. Another one from peanuts, actually. Sorry for giving the same crop twice, but interesting one here because this is looking at harvesting efficiency. I'm sure you're aware that with peanuts, what happens is it's a 2-stage operation for harvesting. The peanuts are lit, the peanut plant is lifted and allowed to dry on the surface before the harvester then goes in to actually harvest the peanuts. Now, particularly when you're working on contours and curved paths and so on, the problem is for the harvesting, the peanut harvester itself, to actually be able to follow along the centre line of the peanut crop. Here, Benedis and his colleagues looked at the difference between using auto steer for the harvester and conventional, i.e. just basically the driver following the line. And you'll see that in 2 years, if you you look along the comparison on the bottom line there, that in both years they got around about a 10% increase in yield simply by going to water steer. So that's significant. Rice is a staple for half the world population and represents 20% of total food energy. Studies on rice here from Simmons and his colleagues, where they looked at temporal and spatial variability in yield over 3 years, and sought to zone the field in terms of soil available phosphorus and soil electrical conductivity. And on the left-hand side there, that's the two zones that they define for their field, where they can vary according to the zoning and get an increase. Challenge availability. Rates of water extraction for irrigation are exceeding rates of replenishment in many places. Inadequate access to safe drinking water is true for about 880 million people in the world, and inadequate access to water for sanitation and waste disposal for about 2.5 billion people. Significant. Groundwater overdrafting excessive use leads to diminished agricultural yields. And overuse and pollution of water resources harms biodiversity, and of course we even get to the stage where regional conflicts over scarce water resource can lead to warfare. In this study by Al-Ghaidi and his colleagues, they looked at zoning based on soil electrical conductivity, elevation, and NDVI. And they basically, in this centre pivot irrigated plot, sought to zone the field so that based on those parameters and see about vary the amount of irrigation water applied and look at the yields. And what they in fact found was that the highest yields were not at 100% of evapotranspiration, but at 70 to 80% in both zones. Again, significant. It really means a 20% saving in irrigation water. That's significant. Challenge number 3, soil quality. Erosion removes topsoil, which often has the highest biological activity, reduces levels of soil organic matter, and contributes to the breakdown of soil structure, which creates a less favourable environment, obviously, for plant growth. Study by Martinez Casanovas and his colleagues looked at detecting ephemeral gullies in minefields. Basically, they used NDVI to determine the crop cover within the gully area, and these gullies form because of high rainfall, high precipitation rates, and farmers don't always take measures to avoid these gullies forming. They also looked at the actual contour of the gullies by using digital elevation models obtained from UAV images. And they were able to show how, they're able to show the decreasing fertility within these gully regions, the importance of control to prevent gully that erosion happening. Challenge number 4. Land availability. The global cropland availability is in decline. Whilst the need for food is increasing, the amount of available farmland per capita is continually shrinking. In 2005, there was still 2,200 square metres of farmland available to supply the needs of one human being. By 2030, it's estimated that there will be only about 1,800 square metres, so a 20% decrease. Some work reported by Nano and her colleagues looked at multi-scale assessment of soil salinisation risk in southeast Sardinia, so an area adjoining the sea where they looked at They looked at exchangeable sodium percent and electrical conductivity to ascertain areas that were at risk of salinisation. So to optimise the amount of land available for cropping. Challenge number 5, pesticide herbicide resistance. Growing number of cases of herbicide resistance. Well, I guess that science-specific herbicide application has been a goal since modern precision agriculture started. Weeds do not grow uniformly, we know that, and the prospective herbicide savings are very great. And yet, we do not see site-specific herbicide application being practiced. And the big problem, the big research problem, of course, has been automatic weed detection. In this particular study, all they were looking for was yellow flowering weeds. So in one sense, that was fairly easy. And they basically were using satellite imagery to determine where the weed patches were, and brought there by Castro and his colleagues. In this case, the actual difference in height between crop and weed was being detected. The brighter areas were with a higher crop, a higher plant rather, which in this case was weed. But again, it's a limited way of detecting weeds. This is not exactly weed detection, but I can't even pronounce the fellow's name, but these researchers were seeking to detect bitter melon and green pineapples within the green background. And basically they're using texture analysis and interest point feature extraction and an SVM, so that's support vector machines, to detect the fruit within the background. And of course that's the problem that one has with weeds, that one's seeking to detect generally a green plant amongst other green plants. And of course it's not only weeds that grow in a spatially variable pattern, but also insect and disease infestation is highly spatially variable. Here in this study by Oka and his colleagues, they were seeking to detect scab disease on apple leaves. Of course, on the left-hand side, the visible image showed no effect whatsoever. But then using thermal imaging, they were able to detect the presence of the disease. So that gives a possible means of detecting disease at early stages before real onset. Challenge number 6, energy cost availability. Energy demand could double between now and 2050. So again, a challenge that needs to be taken seriously. A study here from Denmark by Jensen and his colleagues, where they're looking at the impact of widespread adoption of precision farming and controlled traffic systems in Denmark. And I think controlled traffic systems can most certainly be counted as part of precision agriculture. Here basically, you'll see that they were looking at the effect of applying controlled traffic, centre column, and also controlled traffic, CTF, and precision agriculture in terms of fertiliser and herbicide site-specific application on the right-hand side. And you see how from conventional, they were able to estimate savings, profits of 80%, sorry, 80% change in one case, 120% in the other case. Sorry, not percent, euros per hectare, my units right. A couple of years again in Denmark, this wide-span vehicle was made available. Not quite sure about the take-up of it, but it's basically 9.6 metre track vehicle with the idea that you can plug in different modules, cultivation modules, harvesting modules, spraying modules and so on, and keep your wheelings to set wheelings within the field, just 9.6 metres apart in this case. A colleague of mine, Tim Shaman, has been working on controlled traffic farming for many years, and he's a big promoter of it, and he put together a little animation that I'd like to show you, which shows how this concept can work. So if we could have a video. I hope the technology works. So essentially, this is an animation. So it's basically you have a wide-span vehicle that can adapt to travelling on the road. Comes into the field, and then the wheels can turn 90 degrees. And controlled by hydraulic motors. Similarly, the cab can turn to 90 degrees. And then that vehicle runs across the field, as you see, what a wide span, minimal wheelings. Position controlled by real-time kinematic GPS or GNSS. And similarly, if the field is non-rectangular, then it can compute the most efficient route across the field. Similarly, if there are obstructions in the field, such as a tree, then that is programmed to move around that object. So the idea then is that you can plug in different modules to that wide-span vehicle. There's cultivators, seeders, or a spray boom. Because what's the point of a wide-span vehicle and controlled traffic farming is of course to minimise compaction of the soil. This relates immediately to energy demand. So if we look at, here's some figures that Tim Chairman provided for me. The energy required for cultivation and drilling on a 60% clay soil, so heavy soil, non-inversion tillage with tine cultivators. In the top row, the energy required for non-traffic, controlled traffic farming, and below that for conventional. And you see that the energy requirement, the depth of tillage is slightly different, but the energy requirement is less than half with controlled traffic farming on that heavy soil. So very significant. So CTF is certainly on the way to the future. Next challenge, number 7, environmental protection. Many of the current approaches will continue to degrade the environment and compromise the world's capacity to produce food in the future. A significant benefit of precision agriculture is reduced environmental impact of agricultural operations by reducing agrochemicals and optimizing the use of fertilizer. And of course, in the very extreme, we're talking about mechanical weeding rather than using chemicals and so on. So, for example, here, one example by Norimark and colleagues, where they designed and evaluated an autonomous GPS-based system for intra-row weed control by assessing the tilled area. And essentially, the tracking path of the cultivator, the intra-row cultivator, knows where the plants are and avoids the plants and just tills between. And then a commercial piece of kit that's available in the UK, the Gartha RoboCrop, commercial non-chemical intra-row weeding system. Essentially, you see cameras viewing the crop. The camera is viewing the crop ahead of the machine, and at the rear here are the cultivating tines, the weeding tines that are controlled from the images captured by those cameras. Now, here's just put this on. Right, the camera essentially seeks the centroid of each crop plant, in this case lettuces. And marks that's you see the picture there, marked with a cross. Just got a bit of quick bit of video that just hold on a sec. Oh, there we go. It throws your eyes, I'm afraid. It's just too fast. But essentially, this is in real time, and the cameras are an image analysis software are identifying the centroids of the lettuces. So then that information is then passed through to the cultivating tines, and a short video clip here will show you how it works. Okay, so you'll see the cultivating tines going between the lettuce crop, controlled from the camera information. So that's a commercial system. In this bit of research work by Mann and colleagues, they were looking at delineating productivity zones in a citrus grove using citrus production, tree growth, and temporally stable soil data to define zones so that they can apply site specifically. And those are the zones that they identified, basically fertility, very poor, or medium, good, and very good. Prime productivity zones